All right, welcome back to the C++ course. This is chapter 15, Polymorphism and Virtual Functions. So we've already done kind of the advanced object-oriented programming chapter. I guess this would be the advanced object-oriented programming chapter. Polymorphism, virtual functions, again, is something that exists in a variety of different programming languages. How you express these ideas can vary from language to language, but pretty much all of them will support these things. This stuff, particularly polymorphism, is particularly useful if you are a game dev or if you're more of like a software architect working on large-scale systems, large interconnected complex systems that deal with lots of hierarchies, lots of inheritance, things that subclass other things. So pay attention if that is you. Here's our topic. So type compatibility and inheritance hierarchy. So this gets into the idea of the is-a relationship in terms of the hierarchy. So if you have a player object, a player is an entity, say. An entity is an object. And the higher up you go up this chain, the more generic the classes become. And it turns out that there is some level of compatibility between these classes as you go up the hierarchy. Of course, name of the chapter, Polymorphism and Virtual Member Functions. And abstract base classes, pure virtual functions. An abstract base class, by way of preview, is an idea where you create a class, but you never actually instantiate an instance of this class. The class is intended to be extended and overridden in various ways. You'll see what I mean by this a little later. It's a very, very abstract concept, as the name implies. Again, taking a look at composition versus inheritance, this is something we took a peek at earlier in the course, and we're going to revisit it here in chapter 15. All right, so check out this very, very simple class hierarchy. So type compatibility and inheritance hierarchy. So classes in a program may be a part of an inheritance hierarchy. We know this, we've seen this. We've implemented simple examples of this. So if you have a very parent class called animal, a base class, if you will, two classes that may extend that would be like a particular kind of animal, a cat and a dog, and then a poodle may be a particular kind of dog. All of these would be examples of new classes in your C++ code. Generally speaking, classes lower in the hierarchy are special cases of those above. So a poodle is a special case of a dog, and a dog is a special case of an animal. Now this gets into the compatibility. So if you have a pointer that's pointing to a derived class, you can assign that pointer to the base class. Another way to say it, a base class pointer can point to the derived class object. So an animal, this is a type, remember, animal pointer called PA equals new cat, which is a child class of animal. Okay, you can do that. Those two things are compatible because a cat is an animal. Also, assigning a base class pointer to a derived class pointer requires a cast. So if you have an animal pointer equal to a new cat, then you have a cat pointer. You can do this. You can do this assignment. You can say the cat pointer equals the static cast to a cat, PA, and that'll work just fine. The base class pointer must already point to a derived class object for this to work correctly. Hopefully that makes sense. Let's check out a read-only version of page 965 in chapter 15. Down here. So by the way, this is a file called inheritance4.h. It is just a header file, so it's going to contain both the header information of the class as well as the implementation details. You should be able to find this file in your textbook files that are linked to, or should be included with the book if you purchase that online. But it's right here, inheritance4.h. We're going to be utilizing inheritance4.h and inheritance5.h in some of our future hands-on in the lesson, so keep those handy. Notice we're including string and we're including the memory libraries. Okay, so what are we doing here? Well, we've got some enums. Remember from many chapters ago, enums are basically a way to categorize your named constants. So if you have an enum called discipline, values in the enum are archaeology, biology, and computer science. Classification would be freshman, sophomore, junior, and senior, basically student classifications. And then behind the scenes, remember, each of these names represents a number. And the numbers start at 0. So archaeology is 0, biology is 1, computer science is 2. Same pattern down here for the classifications. Remember from previous classes, previous lessons, that you can sort of override that default behavior, those default integers, if you so desire. So we've got a class person here. We've got a protected member called name. Remember, protected means that subclasses of the person class can access the protected data members. Anything outside of the class hierarchy cannot. Superclasses cannot, but subclasses can access the name property. Then it looks like we've got a constructor here that simply calls setName and passes in the blank string. We've got another constructor that accepts a string reference called pName and simply sets it accordingly. So 2 constructors. We've got our setName, we've got our getName, no surprises there. Here then we have a student class that extends person. So remember, when we extend a class, we get everything that is contained in the person class now in the student class. And because student is subclass of person, it can access the protected string name data member. In the student class, we've got private data members, including the student's discipline, that enum, as well as a pointer to an advisor, pointer to a person rather, called advisor. And this is a shared pointer, okay? But it is a pointer to a person called advisor. Then we've got our public section. We've got our constructor here that accepts, again, a name reference, accepts a discipline enum, this guy here. To construct the student, you can pass in a discipline. You can pass in a pointer to a person for the advisor. And then we call, remember this syntax, we call the superclass constructor passing in the name. Then we do a little assignment here. There's some setters and getters down here, nothing special. Then we have the faculty class, which extends person. Faculty has a discipline enum called department, typical constructor here. Again, we call the base class constructor. We've got a setter, we've got a getter. Then we've got a T faculty, which extends the faculty. So now we're getting a few layers deep. We've got a person. Underneath person, we've got faculty. And then underneath faculty, we've got T faculty. And a T faculty then has a title. It's got its own constructor. It's got a set title method in it. And it also has a way to override get name. Now let me see if we go back a page. Get name is contained in person. Does faculty also have it? No, but person has a get name public method. This is kind of a little preview from where we're showing you where we're going. String get name const return name. All it does is return name. But down here in the T faculty, little comment here, override get name. So here, this thing also has a get name that returns the title plus a call to the superclass person scope resolution operator get name. So this is like adding functionality to the base class get name, if that makes sense. The get name is still being called because we still say person, basically : get name from the superclass, but we're also doing our own thing in here. Cool. So that's kind of just a high-level overview of this inheritance.h that we'll be working with moving forward. Okay, typecast with base pointers. So C++ uses the declared type of a pointer to determine access to the members of the pointed to object. If an object of a derived class is pointed to by a base class pointer, all members of the derived class may not be accessible. Typecast the base class pointer to the derived class via this static pointer cast in order to access members that are specific to the derived class. Overridden functions and pointers inheritance. So if a derived class overrides a member function in the base class, and a base class pointer points to a derived class object, then the compiler determines the version of the function to use by the type of the pointer, not by the type of the object. Read that again if that's confusing. These seem like very complicated and stringent rules, but I promise they kind of just make sense as you're coding. You don't have to think about these ideas too much as you're writing. They're more or less just put here for completeness sake and just to kind of say that they've been said. Okay, let's do a hands-on. 15.1, finally. Okay, so let me clean this up a bit. Yeah, we're going to include that inheritance4.h file. So let's go ahead and include it. I'm going to right-click my header files here. I'm going to add existing item. I'm going to search for this textbook folder. Source code files, chapter 15. There, I've got it. Now I've got it so I can include it. What is it called? Lowercase I. Include inheritance4.h. I wanted to point out I had to pause the video for a minute to remind myself that I needed to pop back over to my solution folder here, right here, and go ahead and copy that inheritance4.h file. Actually physically copy that file over to ex15-1 for Visual Studio to be able to pick it up. Now, unfortunately, it's still giving me the red squiggly, but I think that is what I call a phantom error, because if I go ahead and compile and run this, I still see hello world. This appears to be just a mistake on Visual Studio's part. However, we'll find out for sure once we start actually using objects from that class. So let's create a shared PTR of the person type. IOStream, we need standard namespace. Call it person pointer, shared PTR person pointer. Now let's try to build this again. And it builds just fine. That's somewhat annoying. Identifier person is undefined. Let's keep going. Shared PTR. Faculty PF T faculty. T faculty called PTF. And let's see, PTF equals make shared T faculty. By the way, restarting Visual Studio seemed to fix those phantom squiggly error lines that I was complaining about. So just close and reopen the project and you should be fine. T faculty construct Indiana Jones discipline. IntelliSense picks that up too. : archaeology, life is good. Title, I believe, is the next parameter. Doctor. Excellent. So it says calling pname through a pointer to T faculty uses the version of getName in T faculty. Let's see. Cout. GetName through a pointer to T faculty. Cout. Now remember our special syntax, our arrow syntax. If I say PTF arrow get name, a couple things we need to review here. Remember, that is the equivalent of dereferencing the PTF pointer and then calling dot get name on it. Arrow notation is that cleaned up method of saying dereference then dot some method name. Okay, that's the first part. That's the review. The new piece, though, is you're getting the name through a pointer to T faculty. So calling that, uses the version of getName in tFaculty. So it's using the specific version of getName contained in this class. Next, we can say pf, which is a pointer to a faculty, equals ptf. So we've taken the more generic faculty pointer and assigned it ptf. Now, when we call getName, call getName through a pointer to faculty now, and we're just going to call pf getName. That's going to use the getName in faculty naturally. If we do this, we can say pp equals ptf. Now we've got this very generic, the person pointer equals the pointer to our tFaculty. getName through a cast2 pointer to tFaculty. So yeah, static pointer cast to tFaculty. And here we're going to say pp arrow getName Now, the derived class member can be accessed using a cast. Cool. But wait, there's more. If we have a shared PTR to tFaculty called ptf1, ptf1 equals static pointer cast to tFaculty, pp, then we can access getName through a pointer to tFaculty. So yeah, getName through a pointer to tFaculty. And we'll see out ptf1, error notation, getName, see out an endl, and we'll return 0. Cool. Nothing too mind-bending going on here, just showing you how we can pass pointers and reassign pointers and cast them to different objects up and down the class hierarchy tree. Hopefully we'll see the same output as in the textbook. So we see Dr. Indiana Jones, Doctor, and Doctor. Very good. Okay, if I'm being honest, that's a little bit of what I would call preamble to the main event of this chapter, which is polymorphism and virtual member functions. Knowing these topics will not only make you sound impressive at bars, but will separate the wheat from the chaff in terms of newbie programmers and what I would say are like advanced level developers. So what is polymorphism in general? So polymorphic code is code that behaves differently when it acts on objects of different types. The textbook example of this is, say you have an animal class, superclass, and then derived classes would include like dog, cat, and a cow, say. All of these animals have like make noise, have a make noise method or say hello method or something like that. The methods are all the same names. It's all called make noise or getName or something like that. The key though is when you actually call those methods, when you call a make noise on a cat, the result is different than if you called make noise on a dog or a cow. Even though it's all called make noise, the specific implementation of the make noise method is what changes. And it's what allows you to do things like loop through a collection of animals, even though they have different derived types. They all share the same method name called make noise, and they're all going to behave differently. In terms of video games, where does this come into play? Because it comes into play a lot in game design and game programming. Say you have an enemy base class, and the derived classes are things like ogre, spider, bat. These are very generic enemy types, but all the enemy types that are derived from enemy have some attack method. It's just called attack. The specific attacks that these enemies do will change from enemy to enemy, but it's all going to be the attack method. So what that means is if we have a collection of derived enemy types, we can have a vector of enemies and have bats and mice and ogres in that collection, iterate through the collection, and just call the attack method on them. Easy peasy. That's polymorphism. The alternative to this, and you see this in a lot of like new programmers code, is saying if the enemy is a bat, attack this way. Else if the enemy is a ogre, attack this way. Else if the enemy is a this, do this other thing. Polymorphism, if nothing else, gets you away from having to do these complex if-else statements and switch statements. It's a very clever, elegant way to do this kind of thing. So that's the generic idea. What is a virtual member function? So this is the C++ mechanism for achieving polymorphism. So somehow you have to have a way to do this kind of thing. Like there has to be some syntax in your programming language to allow you to do polymorphic behavior. It turns out in C++ this is called virtual member function. Okay, let's jump into hands-on 15.2. Hopefully this will go a little bit more smoothly in terms of the include. Let's create a new project. Okay. Inheritance 4. Let's include that. Let's add an existing file. Downloads. There it is. Let me copy it into my project folder. Paste it in there. Let's see if Visual Studio picks it up. Looks doubtful. All right, just to show you, I'll just save it, close it, restart it. Probably a more elegant way to do this. Open to suggestions in the comments. Okay, let's build it and make sure it's running. Oh. Inheritance, not inerrancy, inheritance. I can spell inheritance4.h. Good. All right, what else do we need? We need a vector. So the comment here, and it's important to realize, this exhibits the default non-polymorphic behavior of C++. So this is kind of doing it the generic default way. Non-polymorphism going on here. So let's see what that kind of looks like. So let's create, yes, we are in main, a vector of shared PTR of people. So let me digest this for you a little bit after we write it. People. Let's get the semi in there so we don't forget that. Okay, so what is this thing? This is a vector of pointers to persons, to person objects. That's why we need double angle brackets, because we're dealing with pointers and we're dealing with a vector. So we have two sets of angle brackets. Don't let that scare you. So let's make shared T faculty. And just to keep things nice syntactically, drop down to a new line. Discipline, archaeology, title is doctor. Comma, because we're making a list of T faculty pointers. Make shared student, rather a vector of person pointers. Here we go. Thomas Cruise. Computer science. Is that right? And then we're going to pass in the null pointer. Null PTR for the title. No title for Thomas Cruise. Make shared, what do we got here? Faculty. James Stock. Discipline, biology. Another T faculty. Sharon Rock. Discipline is biology. Title is, I'll just say prof. Finally, Nicole Human. Archaeology. Doctor. Good. All right, so check this out. The type of the vector is a pointer to person objects. Okay, so remember the person class is the very most superclass of all these other classes. Faculty, T faculty, and student all derive from person. So we don't have to have just a vector of person pointers. We can have derived class pointers in that vector. That's totally fine. So now, go down here, print names of person objects for int k equals 0. K is less than people.size k plus plus. Cout people at location k. Arrow get name. Endl. And what I want to point out here, notice that the program calls the person version of the getName function for all objects in the array, even though T faculty have their own more specialized version. That is the key with this program. Let's run it. And we're just going to see very generic getName calls. Okay? That's just calling getName from person. The textbook says that some of these have their own special getName calls, their own getName methods that aren't being run because this code is not polymorphic. This is how the default behavior goes if you're just iterating through a collection of derived classes of, in this case, a person object. Okay. So let's take a look at a few more slides here and then we'll do the polymorphic version. Okay. Consider this hierarchy. Animal derived from animal is cat and a dog, and a poodle derives from dog. So the animal, cat, dog hierarchy where each class has its own version of the member function ID. Okay, so the animal class has an ID. The member function ID, or the method ID. So animal has a method called ID, cout animal. The cat, which extends animal, has its version of ID, which prints cat. It doesn't print animal, it prints cat. Then the dog prints dog in its version of the ID method. Consider a collection of different animal objects. Okay, that's fine. We just did this more or less in the previous hands-on. So we've got an array of animal pointers called PA. Inside of that, we're going to create a new animal, a new dog, and a new cat. So three types here in the animal array. If we do this, if we loop through just like we did in the previous hands-on, PA at location K, arrow ID, is going to print animal, 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 ignoring the more specific versions of ID for dog and cat. These two are not being run. It's all animal. Preceding code is not polymorphic. Right. It behaves the same way even though animal, dog, and cat have different types and different ID member functions. The polymorphic code would have printed animal, dog, cat instead of 3 prints of animal. The code isn't polymorphic because this expression, in that expression, the compiler sees only the type of the pointer PAK, which is a pointer to an animal. The compiler doesn't see the type of the actual object pointed to, which could be either of these 3, animal, dog, or cat. Enter virtual functions. So if you declare a function virtual, it will make the compiler check the type of each object to see if it defines a more specific version of the virtual function. This makes the function, in my opinion, smarter. This says, hey compiler, don't assume that this is just an animal type. Check to see if there's a more specific version of the getName or ID method in a derived class. Okay. If the member functions ID are declared virtual, then the code, this, will print animal, dog, and cat. I'm thinking, yes, on this slide you can see what that looks like. So how do you declare a member function as virtual? Well, you say virtual. In true C++ fashion, if you want to do something, you just say that thing. So here is our animal class. Here's our ID method, which we've said is virtual. Likewise, with our cat, we've said this ID method is virtual, and with the dog, this method called ID is also virtual. Let's try it on page 972. And in this case, we've got inheritance 5.h. There's my include. We need memory. Oh, I'm sorry. This is inheritance 5.h. Let's just take a look at it instead of retyping all this out. I believe we'll use inheritance 5.h later, but let's just take a peek. Yeah, there's not much changed here. In it, the getName function of the person class has been declared virtual. Yeah, otherwise nothing has changed. It includes the inheritance 5 file, which is just the inheritance 4 modified to make the getName in the person class virtual. So we can see that right here. We've got person, we've got virtual string getName. Inside of student, which extends person, we have getName, getMajor, setAdvisor, getAdvisor. T_faculty, yes, right here. Virtual string getName. So if we have a collection of all different kinds of objects, including T_faculty, which extends faculty, when we say T_faculty, whatever instance you happen to be, getName, because it's been declared virtual, the compiler will say, hey, maybe there's a more specific version of getName inside of T_faculty that I can use. Sure enough, there is, and it'll go ahead and use it. Okay, this demonstrates the polymorphic behavior of C++. Now we have the same vector of person pointers that we had earlier, same types of data included inside of that vector. And in fact, we even have the same loop. Not even the loop has to change. What changes are the definitions of the methods in the classes themselves that cause the behavior to become polymorphic. Now you can see that we have a much smarter version of getName in the program's output. That's all polymorphism is. It's this big, scary, maybe sounding term, but under the hood, it's really not that difficult. You just have to use virtual functions. Okay, so a few notes on function binding. So if we say things like PA at location K, arrow ID, the compiler chooses which version of ID to use. Different versions in the animal, dog, and cat classes. Now, function binding is the process of determining which function definition is to be used for a particular call. There's two alternatives, static and dynamic. In static, you choose the function in the class of the base class pointer, ignoring any versions in the class of the object actually pointed to. Static binding is performed at compile time. With dynamic, the function invoked is determined at execution time. I know, shocking, dynamic versus static. You can look at the actual class of the object pointed to and choose the most specific version of the function, and dynamic binding is used to bind virtual functions. So that makes me think of these two words, overriding versus overloading. If you remember back from when we first started talking about functions many lessons ago, we talked about overloading a function. And if you remember, overloading a function is where you have two or more functions with the same name but different parameter lists. So you have a function that has the same name but maybe one of the versions accepts one parameter and another version accepts 3 or 4 parameters. Okay, that is overloading the function. But overriding basically takes a function and extends on its functionality, what it does. Suppose a derived class is a function that overloads a virtual member function in the base class. If you want the derived function to override the base class function, use the override keyword at the end of the function header or prototype. This indicates it should be treated as an overriding function instead of an overloading function. And the final keyword and overriding. So the keyword final can be used at the end of a header or prototype of a function in an inheritance hierarchy if you want to ensure that no classes below this one overrides this function. Hence the word final. This says this is the end of the road. Nobody else can override it. If an attempt is made to override the function in the derived class, a compiler warning will occur. Let's hop on over to 976. And let's see what we're dealing with. Yeah, it demonstrates the override keyword. Not much to include here. Okay, just a simple little hierarchy. So here's a class called base public virtual void function A, passing in an int arg const. And let's see, what is it going to do? It's going to see out, this is base function A. Here's a class called derived, which extends public base. And it's got a public section, virtual void function A, also accepts int arg, const override, keyword. See out, this is derived function A. Endl. Now, what's this complaining about? Public base, yes. All right, so we're in main now. Got our little hierarchy created. Here's a shared PTR type base, BASE, called B equals make shared derived, and a call to a virtual function A through the base pointer. So we can just say B arrow function A, passing in 99 or something, return 0. Let's activate, run, and we should see derived function A. Very good. Okay, and now abstract base classes. This is kind of cool stuff. And pure virtual functions. So an abstract class is a class that contains no objects that are not members of subclasses. For example, in real life, animal is an abstract class, but there are no animals that are not dogs or cats or lions. I think of abstract classes as just like a logical class, like it's just a way to abstract away common pieces of data and functions, but you would never actually create an instance of an animal. If you think about real life, you never see creatures outside walking around. You just say, hey, look, animal. You see it. You say, hey, look, dog. Hey, look, there's a cat. Hey, look, there's a bird. Not, hey, look, there's animal. Maybe you say, hey, there's an animal. I don't know what it is, but it's always going to have some concrete type to it. It's never just going to be an animal. It's going to be something more specific. But there is something about all animals that is shared in the animal class or in the animal idea, what it means to be an animal. There are commonalities there. Yeah, so this is good. Abstract classes are an organizational tool. They're useful in organizing inheritance hierarchies. They can be used to specify an interface that must be implemented by all subclasses. Keyword interface. Along with that, we get into pure virtual functions. So the member functions specified in an abstract class do not have to be implemented. The implementation is left to the subclass. A function without an implementation is a pure virtual function or an abstract function, and in C++, an abstract class is a class with at least one abstract member function. What this is saying is, in the base abstract class called animal, maybe there is a make noise function, but that function doesn't actually have any guts to it. It doesn't have any implementation. The implementation of make noise is left to the specific subclasses that inherit from that function, if that makes sense. It's sort of like setting up a contract and saying, hey, there's this function that all of my subclasses must implement, but I, in the base class, am not going to implement it. I'm leaving it up to you, so all subclasses, to go ahead and say what it means to make noise. So in C++, a member function of the class is declared to be an abstract function by making it virtual and replacing its body with, in pure C++ fashion, equals 0. There's no keyword involved here. It's just saying virtual void ID equals 0. Other languages do this differently and better and more explicitly, in my opinion. Other languages use a term called interface to do this. They have a dedicated keyword to do this. In C++, we have equals 0. So, okay, fine. An abstract class cannot be instantiated, can only be inherited from, you can only derive from it. Classes derived must override all pure virtual functions with concrete member functions in order to be instantiated. The abstract class says, hey, derived classes, you must instantiate these functions. You must implement these functions. If you do not, there's going to be a problem. It's like a contract that the abstract class has with all the subclasses that inherit from it. Let's check out 978. Cool. So we've got IOStream, memory, and vector. Let's just read through this guy. Demonstrates an abstract base class and pure virtual functions. So we have an abstract base class, yes, called shape. Okay, you would never create a new instance of a shape. In real life, you never sit down and say, I'm going to draw a shape. I'm going to draw a triangle. Yes, I'm going to draw a circle. Not, I'm going to draw a shape. So it's our base class. It's our abstract class. But all shapes must have a position X and a position Y. All shapes must know how to draw themselves. Okay, this is what we were talking about in the slides. Virtual void draw equals 0. So the shape base class doesn't know how to draw itself, but all subclasses of shape must know how to draw themselves. So here's a rectangle. Here's where it's implementing its draw method, saying virtual void draw, and here's what it means to draw a rectangle. Imagine it. Here's a hexagon. Here's what it means for a hexagon to draw itself. And inside of int main, we're creating a vector of shared pointers of type shape. And we have a hexagon, a rectangle, and a hexagon. Since they're all sharing the subclass of shape, we have the position X, position Y. We can loop through the collection, and we can set the positions, do whatever we want to with them. And then here's the polymorphic behavior. We can just say all shapes, arrow, draw, and each specific version of the shape will use its own specific version of draw. Polymorphism in action right here. Okay, a few words on composition versus inheritance. Remember, inheritance is a relationship between classes. An object of a derived class is an object of the base class. For example, an undergrad is a student, a mammal is an animal, a poodle is a dog. When defining new classes, composition is good when the new class needs to use an object of an existing class. Inheritance is when objects of the new class are a subset of the objects of an existing class, or the new class will be used in the same way as the object of the existing class. 985. Yes, demonstrates the is a relation in inheritance. So nothing special in the includes, but we do have a base class called dog, and all dogs have a weight. They have a constructor. Here's a virtual void bark function. Here's a sheepdog, which is a special type of dog, and it's going to have a number of sheep, I guess, that it's responsible for or something. It overrides the base class bark method, so it has its own special bark. And that's the only two classes we have. We create a vector of dog pointers. We create a dog, we create a sheepdog, we create a dog. We walk by each kennel and make the dog bark. Oh, how creative. Okay, so we have a dog saying its thing, a sheepdog saying its thing, and a dog saying its thing. I want to point out again the benefits of polymorphism. In this loop, we don't have to check to see if we're dealing with a dog object or if we're dealing with a sheepdog object. We don't have to waste our time with that series of if, then, or switch statements. The polymorphism takes care of that for us. Thankfully, it's a very, very, very nice feature to have. Finally, the case study of the chapter, Secure Encryption Systems. So, a recently founded consulting company that advises businesses and corporations on how to protect their data from unauthorized access. So we're going to use virtual functions and abstract classes to build an application framework. What is that? It's regarded as an application in skeletal form, only needs user to specify the definition of a few functions to transform the framework into a useful application. It's like an abstracted application. So it's a simple little encryption framework here. We've got an input file and an output file, and we've got encrypt and decrypt functions, which will do the actual work of encrypting and decrypting, whatever that is. I'm assuming the method that we're actually using to encrypt and decrypt is pretty elementary. Looks like it here. Yep, the file cannot be opened. Do work. Let's see, where's encrypt? Here's a constructor. Let's take a look at the encrypt function right here. Here we go. It looks like we're calling, so we're looping through the characters in the file that we're trying to encrypt, and we're calling this transform function. Let's see if we can find the transform function. Right here. In simple encryption, there is a transform function. Right here. And all it does, the method of encryption we're using, I guess, is just taking the character +1, so taking the character's ASCII code and adding 1 to it. So the point of this isn't to come up with some robust encryption scheme that can withstand the efforts of the United States government trying to crack it. The real emphasis of this exercise is to make sure that you can understand how this application framework fits together. The encryption scheme is a joke. So we're adding 1 to the ASCII value to encrypt. The key, though, is can you understand how all the parts of this framework fit together? And I think based on our previous study of the chapter, it should be pretty straightforward to do so. That's going to wrap it up for chapter 15. We must have made it through in record time, less than an hour at this point. So the remaining chapters of the textbook seem to be more or less advanced topics and one-off topics. So they're taking less time than our slog through functions and if statements and things like that. I hope that's a benefit to you. If you have any questions or comments, hit us up on the YouTube channel in the comments section. Otherwise, we'll see you right back here for the next chapter, chapter 16. Thanks so much.